Yes, the metal water piping can be bonded to the MLO panel grounding conductor. The metal water piping must be bonded to the grounding conductor at the MLO panel using a bonding strap as specified in section 250.104A of the National Electrical Code. The bonding strap must be sized as per table 250.122, based on the size of the main service conductor. In this case, since the main service conductor is 4/0 American wire gauge aluminum, that requires a bonding strap of at least number 4 American wire gauge copper. No, you do not need to increase the size of the grounding conductor back to the service disconnect per section 250.66 of the National Electrical Code. Section 250.66 applies to systems with a single equipment grounding conductor that serves as both the grounding electrode conductor and the main bonding jumper. In your case, there is a separate grounding electrode conductor which is number 6 copper and a separate main bonding jumper which is the bonding strap from the water pipe to the MLO panel grounding conductor. Let's get into a clarification of sections 250.104A1 and 250.104B. Section 250.104A1 requires that metal water piping that is present on the premises and likely to become energized be bonded to the system grounding conductor at each service, feeder, or equipment entrance. Section 250.104B requires that the bonding means be installed in a manner that creates a permanent and continuous bond. It also prohibits the use of the neutral conductor as the bonding means. In this specific scenario, the metal water piping is likely to become energized due to its proximity to the electrical system. Therefore, it must be bonded to the MLO panel grounding conductor at the panel entrance. The use of a bonding strap meeting the requirements of section 250.104A will fulfill this requirement. Now let's delve deeper into grounding and bonding, elaborating on each aspect with more technical detail. Firstly, grounding and bonding are two distinct but related concepts in electrical systems. Grounding refers to connecting electrical equipment and systems to the earth. Bonding involves connecting different metallic parts of an electrical system together to create a low impedance path for fault current. The purpose of grounding is to provide a path for fault current to return to the source, allowing overcurrent protection devices such as circuit breakers or fuses to operate and clear the fault. This helps to protect people and equipment from electrical shock and fire hazards. Grounding also helps to stabilize voltage and reduce electrical noise in sensitive electronic equipment. The grounding electrode conductor, or GEC, connects the electrical system to the grounding electrode, which is typically a ground rod, ground plate, or underground metal water pipe. The size of the GEC is determined by the size of the service entrance conductors, as specified in Table 250.66 of the National Electrical Code. Bonding is essential for creating an equipotential plane, which means that all metallic parts of the electrical system are at the same electrical potential. This reduces the risk of electric shock if someone comes into contact with two different metallic parts that are at different potentials. Bonding also helps to reduce electromagnetic interference, or EMI, which can disrupt the operation of electronic equipment. The main bonding jumper, or MBJ, connects the grounded conductor, typically the neutral, to the equipment grounding conductors at the service equipment. This provides a path for fault current to return to the source. Equipment grounding conductors, or EGs, connect the non-current carrying metallic parts of electrical equipment, such as enclosures, raceways, and motor frames, to the grounding system. The size of the EGC is determined by the size of the overcurrent protection device protecting the circuit, as specified in Table 250.122 of the National Electrical Code. Now let's focus on the specific situation of bonding metal water piping. As discussed earlier, Section 250.104A of the National Electrical Code requires that metal water piping systems be bonded to the grounding system. This is because metal water pipes can become energized due to faults in the electrical system, creating a shock hazard. The bonding connection must be made within 5 feet of the point where the water pipe enters the building. If there is a water meter or other insulating fitting in the water pipe, the bonding connection must be made on both sides of the fitting. The bonding conductor must be sized according to Table 250.122 of the National Electrical Code, based on the size of the service entrance conductors. In the provided scenario, the service entrance conductors are 4/0 American wire gauge aluminum. According to Table 250.122, this requires a minimum bonding conductor size of number 4 American wire gauge copper. The bonding conductor can be connected to the water pipe using a bonding clamp or other approved fitting. It is important to ensure that the connection is tight and corrosion resistant. Now let's clarify the difference between a main lug-only panel, or MLO, and a main breaker panel. An MLO panel does not have a main circuit breaker. Instead, it has a set of main lugs that are used to connect the panel to the service entrance conductors. A main breaker panel has a main circuit breaker that can be used to disconnect the entire panel from the power source. In the provided scenario, the MLO panel is located 30 feet inside the dwelling and is fed by 4/0 American wire gauge aluminum conductors. The grounding electrode conductor is number 6 American wire gauge copper and is connected to 2 ground rods. The question asks whether the metal water piping can be bonded to the MLO panel grounding conductor, and if so, how it should be sized. As discussed earlier, Section 250.104A of the National Electrical Code requires that metal water piping systems be bonded to the grounding system. Therefore, the metal water piping can be bonded to the MLO panel grounding conductor. The bonding conductor must be sized according to Table 250.122 of the National Electrical Code, based on the size of the service entrance conductors. In this case, the service entrance conductors are 4/0 American wire gauge aluminum, which requires a minimum bonding conductor size of number 4 American wire gauge copper. The question also asks whether the size of the grounding conductor back to the service disconnect needs to be increased per Section 250.66 of the National Electrical Code. Section 250.66 of the National Electrical Code applies to the size of the grounding electrode conductor for alternating current systems. It states that the grounding electrode conductor must not be smaller than specified in Table 250.66. based on the size of the service entrance conductors. However, Section 250.66 does not apply to the bonding conductor for metal water piping. The bonding conductor for metal water piping is sized according to Table 250.122 of the National Electrical Code, as discussed earlier. Therefore, the size of the grounding conductor back to the service disconnect does not need to be increased per Section 250.66 of the National Electrical Code. Now let's delve into more specific details regarding grounding electrodes. Grounding electrodes are essential components of an electrical grounding system. They provide a physical connection to the earth, allowing fault current to safely dissipate. There are several types of grounding electrodes commonly used, including ground rods, ground plates, and metal water pipes. Ground rods are typically made of copper or copper-clad steel and are driven into the ground. The length and diameter of the ground rod must meet the requirements of the National Electrical Code. Ground plates are typically made of copper or steel and are buried in the ground. The surface area of the ground plate must meet the requirements of the National Electrical Code. Metal water pipes can also be used as grounding electrodes, provided that they meet certain requirements. The water pipe must be in direct contact with the earth for at least 10 feet and must not have any insulating fittings or joints. In the provided scenario, the grounding electrode conductor is connected to 2 ground rods. This is a common practice, as it provides a more reliable grounding path. When using multiple ground rods, they must be spaced at least 6 feet apart. The grounding electrode conductor must be connected to each ground rod using an approved fitting. Now let's discuss the importance of proper grounding and bonding in electrical systems. Proper grounding and bonding are essential for protecting people and equipment from electrical shock and fire hazards. They also help to reduce electrical noise and improve the performance of electronic equipment. A properly grounded and bonded electrical system provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices to operate and clear the fault. This helps to prevent electrical shock and fire hazards. Improper grounding and bonding can create a dangerous situation, increasing the risk of electrical shock and fire. It is important to ensure that all electrical work is performed by qualified and licensed electricians who are familiar with the requirements of the National Electrical Code. Now let's consider some common mistakes that people make when grounding and bonding electrical systems. One common mistake is using undersized grounding and bonding conductors. The size of the grounding and bonding conductors must be determined by the size of the service entrance conductors or the overcurrent protection device protecting the circuit, as specified in the National Electrical Code. Another common mistake is failing to properly connect the grounding and bonding conductors. The connections must be tight and corrosion resistant to ensure a reliable grounding path. Another common mistake is using improper grounding electrodes. The grounding electrodes must meet the requirements of the National Electrical Code and must be installed in a manner that provides a reliable connection to the earth. Another common mistake is failing to bond metal water pipes and other metallic components of the electrical system. All metal water pipes, gas pipes, and other metallic components that are likely to become energized must be bonded to the grounding system. Now let's delve into the specifics of Table 250.122 and Table 250.66 of the National Electrical Code. Table 250.122 is used to determine the size of equipment grounding conductors for alternating current circuits. The size of the equipment grounding conductor is based on the rating of the overcurrent protection device protecting the circuit. For example, if a circuit is protected by a 20 amp circuit breaker, the minimum size of the equipment grounding conductor is number 12 American wire gauge copper or number 10 American wire gauge aluminum. Table 250.66 is used to determine the size of grounding electrode conductors for alternating current systems. This table provides the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. For example, if the service entrance conductors are 4/0 American wire gauge copper, the minimum size of the grounding electrode conductor is number 2 American wire gauge copper. It is important to note that these are just the minimum sizes required by the National Electrical Code. In some cases, it may be necessary to use larger grounding and bonding conductors to ensure a reliable grounding path. Now let's discuss some additional considerations for grounding and bonding in specific applications. In agricultural buildings, special attention must be paid to grounding and bonding due to the presence of livestock and the potential for corrosive environments. The National Electrical Code provides specific requirements for grounding and bonding in agricultural buildings. In healthcare facilities, special attention must be paid to grounding and bonding to protect patients and staff from electrical shock hazard. The National Electrical Code provides specific requirements for grounding and bonding in healthcare facilities. In industrial facilities, special attention must be paid to grounding and bonding due to the presence of heavy machinery and the potential for high fault current. The National Electrical Code provides specific requirements for grounding and bonding in industrial facilities. Grounding and bonding are also crucial for sensitive electronic equipment to minimize electrical noise and prevent damage. The effectiveness of a grounding system can be verified through testing, including impedance measurements. This testing ensures that the grounding system meets the required standards for safety and performance. Regular inspections are recommended to maintain integrity. Electrical codes, such as the National Electrical Code, are regularly updated to reflect changes in technology and best practices. Staying informed about these changes is crucial for electrical professionals. Many resources are available for learning about grounding and bonding, including textbooks, online courses, and industry publications. Continued education ensures competence. In summary, understanding and implementing proper grounding and bonding techniques are vital for electrical safety and the reliable operation of electrical systems. Following the guidelines provided in the National Electrical Code and seeking guidance from qualified professionals are essential steps.